quickly. And hello, everyone. Welcome and thank you for joining us today for the first session of our webinar series, which is we planned three of them. You informed to the link, and this is the Master of Material Intelligence, Infinite Element Analysis with Total Materia. So my name is Zaim. As you know, I've been working for Total Materia last 7 years, and that's how I met with very valuable and amazing engineers here today with us, Erdi and Bartu. And I'm so excited to guide you to today's session, focus on introducing Total Materia to FEM software users. In this session, we'll begin by exploring the fundamentals of analysis, producers, and the core concept behind nonlinear modeling. We'll take a closer look at the critical material properties that drive accuracy, infinite element solvers, and wrap up with a practical discussion on frequency response in analysis in Nastran. Nastran is one of the most widely used solvers in this industry. That's why we choose, Mr. Ado choose for this session.
Often used for frequency responses or model analysis because
Yeah.
this might be actually
I know. So you're the master of this solvers. Thank you very much for this. It's going to be very educative and so much information that we are going to share with you guys. And whether if you are a simulation engineer, material specialist, or a design analysis, this session will show you Total Materia supports you in achieving more reliable and efficient simulations. Let's get started with our speakers. Well, we have two special guests today, Mr. Erdido and Mr. Bartos Suleimanoglu. I'd like to ask you, each of you, to briefly introduce yourself, where you're currently based, what your role is, how your journey starts with FEA begin, and little about your background.
Yeah, as you know, I have a very handsome picture in here. So I have a 12 years experience on FEE. So I have expert level knowledge of Abacus implicit explicit analysis, but not only Abacus, actually I also have Nastran and Elestina knowledge, but also the other preprocessors, for example, like Plumage and Anza. So what I'm doing right now, I'm not working anywhere for now, which means unemployed. So for the this is my actually the special area that the dynamic and thermal behavior of materials, and focusing on integrated optimization loops with the Python scripting actually. And that's all. Actually, I'm working on over 12 years on finite element analysis. That's all for me. So what about
been 6 years? I think it's been 6 years or something that when we met, and I learned about you a lot about you, and you have classes. Basically, you're also teaching some students about this simulations and so details, right? You've been working with some universities in Turkey, as far as I remember, right?
Yeah. University. I had been worked as a part-time lecturer, actually.
Worth mentioning. I know, that's great. That's great. Thank you.
Okay, so Bartu.
Yeah, hello. I'm Bart Schrimmel. I think I cannot see. Yeah. So I'm Bart Schrimmel. I'm junior structural analysis engineer. So I cannot say that I have expert knowledge when there's a RD round. So
not 12 years maybe, huh?
Yeah, not 12 years. Yeah. All so I know Abacus implicit and explicit analysis. I have some experience in Elestina as well. So I did my. I'm right now currently in England, where I graduated from masters in advanced lightweight and composite structures from Cranfield University. So in my master's thesis, I worked on inverse design of metamaterials with geometric deep learning algorithms. Other than that, when I was in Turkey, I worked as a structural analysis engineer in a consultancy company. So I think that's it right now.
I don't think that's it. You have also lots of impact analysis experience.
Yeah, of course. I can.
Yeah, you see.
So
worth mentioning also experience.
So it's just. I think I would say that my master's was mostly biased on the impact analysis on Elastine and Abacus. So it's just about the composite structures. Other than that, in my bachelor's thesis, I worked on impact analysis as well. So yeah.
One last thing I would like to add to you, you are also unemployed. Bart, welcome to my.
Yeah, I'm looking for a job. I'm looking for a job.
Okay. Here's the thing. We have two very much experienced simulation structural analysis engineer here, and I know Erdi by choice he's unemployed, and Bartu is busy with his thesis right now in the university. So so that's the brief explanation. So remember, this is the first session, and we will go into deep of national level and some details, and we will have next session next week on Thursday, 8th of May, and then third session will be on 15th of May again and Thursday. So you can register with the same link to the others. I think it will be very, very interesting for you to learn all this stuff. So please go, Erdi. You have a lot to talk about this detailed calculations, how material information is helping basically for the accuracy of this simulations. So
yes, thank you, Zaim. So this is just an introduction of the webinar series. The second and the third one will be much more fun, actually. So much more deep dive, really go for it. But this is just the introduction. That's why we are just clean as much possible for this presentation. Okay.
Great.
Well,
we'll refresh our knowledge as well. I learned a lot.
Yeah. So, okay, here we go. What we have got here, there is a workflow of analysis procedures. So you begin with a part, property assembly, some interactions, boundary conditions, mesh, and the results also. There's some steps you need to be taken into account. So all these parts need to be, all these sections need to be constrained as a different perspective. So with the material characterization, there is a common sense that in FAE work that it says that garbage in, garbage out. So when you go for an input as a garbage, you also your result also as a garbage. So you need to select really good inputs, and also it's included as material actually. So what we have here, we have some steps that you can consider about some historical events on your part or assembler system. So you may have a preload or some spring bags after that, but you need to consider about that which part is really important for you. Are you looking for a manufacturing effect on your part, or looking for another spring back effect, or just the strength of your part? Actually, you need to consider yourself and which participant of these historical events need to be considered actually. So we have procedures that we can just separate two sides, which is the linear perturbations and the basically general approach. So as you can see, there is a differences between these symbols. So this means a historical dependency on that marker. As you can see with the previous slide, that there is a history in here. But with this symbol, we can go for it. For example, you are doing a analysis, and the analysis series that you just want to look after spring back model shapes. for example, these are the linear perturbation analysis. So it is not affect the whole process. You just take a look what is going on here. So it assumes the linear analysis, such as the natural frequency extraction, such as the response spectrum analysis or random response analysis. For these it is not a history dependency here. We can assume that these are the linear perturbation analysis. So in the right side, we can just look for the little bit differences in here. As you can see, there is an implicit and an explicit word in here. So this means a really different equation approaches. So in implicit, Bartol already Bartol will also mention about it with the maybe the differences between implicit or explicit. Is it okay, Bartol, in your vibrations page? You may also mention about it. What
yeah,
the differences
okay.
between
We can. I think we can talk in methods when solving nonlinear equations.
Okay, okay. I will not so deep dive right now. Okay, so it will be totally different actually, and also it will require a different material characterization approach, I would like to say, such as if you are go for the heat transfer, you need a different material properties. Maybe you can just go directly just linear static analysis. So maybe you don't need to define your density for your material if you don't have any gravity load, for example. So here we are. And another thing is the, a mesh is a really a team player actually in our analysis. So you should consider what is mesh and what is element IDs, what is node IDs, how it will be a perfect match. We need to consider about it. So we are just looking for a mesh right now, and we can just see that there's also, yes, quads and rectangular areas in here. Okay, but there is also another perspective for the element types we need to consider about it. So which formulation, which degree of freedom, or how it affect our total analysis procedures. So this is also another challenging issue. But not only knowing the element types and behaviors, but also you need to control your mesh workflow. I mean, the technique and algorithm you need to consider about it. This is just how can I say? This is just an introduction to analysis procedure. We will just deep down the other things actually. So I actually write down some solid element selections summary. You can just see the table that which best element choice or which is the avoiding using. You can also get this presentation from Zaim, just mailing him, or you can also I think we will also share some input data for this webinar and other webinar series.
Yeah. After last year's session that we made such a thing, like similar something, and so many people asked that too. That would be amazing.
Yeah. So it's, I will just write down in here, and you can just check it actually. So what we have here, a concept of nonlinear modeling. So as you can see, we can just we have a beam in here, we have a load in here. We already know that this motion, this deflection will be a nonlinear behavior at the end if we have an over deformation in here. We can just assume as a linear if it is this P load is very low, but in the real life it will be a nonlinear. So this is just a very simple, very simple terms of the nonlinearity, but we can just say lots of things actually. So we will also say about the nonlinearity, other material also boundary or other things. So okay, I'm talking too much, sorry about that. Maybe you can just go on.
No, it's not important. It's not a problem. Please go on. I don't want to disturb you. You're going well.
You can do it in here. So actually.
So so we have 3 different nonlinearity causes of nonlinearity. For it could be from the geometric nonlinearity, material nonlinearity. Maybe it's like a plasticity or another nonlinear model, or it could be on the boundary conditions. The contact problems with friction will induce a really highly nonlinear simulations. So I think, yeah, you can model at some point as a linear, but after some displacement values, everything goes to nonlinear, I would say.
Yeah, actually, we basically have 3 types of nonlinearity we can consider: geometry, material, and the contact. Actually, before we go deep down the whole things on the analysis, we may just considering which type of nonlinearity we need to assume actually. So there is the 4 mechanism that we can consider about it, if it is all nonlinear or linear. So we can just ask ourselves, it is scaling or superposition or history dependency. You can just consider about it, which effect could be nonlinear or linear actually. So sorry for interruption, Bart, please go on.
So in order to solve the nonlinear models, we need a different type of approach. So in the implicit, I would say, implicit finite element method, if you have a nonlinear material model, you don't have a constant stiffness, tangent stiffness, right? So how could we do it? We will use Newton-Raphson to model these kind of for these problems, so that stiffness matrix, tangent stiffness matrix could be found for, I would say, plastic region of the material, which is not constant, as you know, after the elastic region. And also, by the way, there's some kind of problems that it could be a problem for Newton-Raphson, which is bistable structures. So in the bistable structures, maybe you know that there's a sudden softening. So because of that, Newton-Raphson will, I think, convergence issues. So in that, the arc length method is used.
Yeah, actually, it's not only for the material causing, but also the other made snap-through analysis, for example. You know, there is also a whole analysis procedure can be as a linear material model, but as you know, that the snap-through is stop fitting if you consider about it. So there should be a softening force in here. The problem is catastrophic. No.
Yes.
So okay, I'm keep going. All right. So basically, as we already mentioned about the step idea, that we have some steps, that history dependency. So Bart mentioned about it, the increments, the iterations under the increments actually. So Newton-Raphson has iterative solutions, iterative numeric analysis in here. So we have some increment method. We need to have increment method because we cannot just go there this point, just the one jump. So we need to be reduce our total load. So we have some fraction of the load, and at the end we have some residues. So we need to add iteration and correction, and we will just have the point. And next we will go for the another increment. If it is not converged, we will have to reduce or increment, and so on. So these are the actually implicit Newton-Raphson method approach. So the impact, we will also mention about the third phase, the impact analysis in Elastina. So we will go deep down into the implicit analysis, the second phase, the metal forming in Abacus actually. So this is just the introduction basically. So what I've got here is the geometric nonlinearity. This is really a very common example for the nonlinear geometric behavior. As you can see, there is a membrane in here. Membrane means there is no rotational degree of freedom on that. It's a cloth, something like that. You can assume that that's a cloth that, and you just clip in here with the whole boundary. So you have a payload and the nodal force in here. So if we constrain there, it should be linear analysis. We can get the second picture, which is not real actually. But if we go for the geometric nonlinearities feature in here, we can say that because of the membrane approach that there is a force and there should be tension in here. That's why if we go for the linear analysis, some examples, we can just get much more displacement. So we need to avoid it. But some cases, it could be opposite sides. Sometimes if you open the nonlinear geometry, you can just get the much more displacements on your geometry actually. The second one is the contact. We will also mention about the other webinars. So this is a really challenging that you need to consider the whole contact algorithms that need to be taken into account. I will mention about the maybe next week. It will be much better, much more suitable for the metal forming actually. So maybe Bart, you can go on in here if you want.
Yeah. So for the as we mentioned for the third nonlinearity, we have material nonlinearities. As you can see in the right side, we have a plastic deformation of a material. So can we please go to the other section? Yeah. So we have it in here for idealized material behavior, but I want to really talk about the elastic perfectly plastic section, because it's when we talk about the implicit analysis, the elastic perfectly plastic materials could cause convergence issues, because there's a, as you can see, there is no tangent stiffness in the elastic perfectly plastic. So when you're using Newton-Raphson method, sorry.
So this means that there is no stiffness actually. So there is no any rigid. Yeah, there is just something in air.
Yeah, the stress is not going high, so there's no hardening. So because of that, in order to model or avoid the unconvergence issues, you could apply slight hardening, really slight hardening in order to solve that. So, but when you think about it, it becomes a bilinear model, like a bilinear model. So other than that, is bilinear model is could be used, but it is up to you. It is because you're just simulating something to find out in the real world application. So if you're thinking that the degree of plasticity is not that really important, or the hardening or the other effects, maybe you can use it, but you need to take many things into account, I would say. Correct me if I'm wrong, Erdi. So
I will something about it. Sorry for interruption, Barto. Yeah, and the elastic to plastic area can cause a nonlinear material convergence issue.
Yeah.
There is actually a common mistake that there is an elastic perfectly plastic or something like that. So as you can see, there's too much stiffness in here. When you go through to the yield point, that is a very less stiffness in here. This point can cause a material nonlinearity problems. So you may also, if you want to stop your ultimate stress in here, maybe you have done all the whole total strain we got. If you end your data point, for example, if you go for the Marlowe method, what is the point-to-point plasticity method? So if you end in here, so you will get at the end perfectly plastic behavior beyond this point. So you may also manipulate your material data that the same tangency can be held and the really a big strain can be defined in here with the same tangency actually. So, please go on, Barto.
So for nonlinear strain hardening, what you can use is maybe, which is well known, is voice material models or Johnson-Cook plasticity models, which is really well known and
yeah, very popular. I know.
Yeah, it's really popular and it has a really big data.
So many questions about it. I know. But those values are not actually same in whole materials, in different sources giving you different Johnson-Cook models and so many information, which is very hard to find which one is the accurate one,
Yeah.
That's why we have secrets, Zaim, by the
way.
In the second
I know. That's the secret of your magic right here. So I understand.
For example, I don't want to go deep dive. I don't want to go deep dive. Sorry.
I know we only have 1 hour the max, so it's not enough for covering only for that topic. I know.
Yeah. Okay. So
please, sorry to interrupt.
Yeah. Okay. Please go on, Bartu. Sorry.
So for this, I would say it's we said that it's an introduction, so it's a preliminary. I think everyone knows the definition of stress and strain. I think the stress is the load divided by area, or strain is the amount of elongation for each unit length. So we can go on. I think. So I think the Poisson ratio is really important topic. As we know that most of the time when we're dealing with metals, what we're seeing is like it has a range of theoretically the Poisson ratio has a range of -1 to 0.5. So most of the time we are using the positive values, but for other materials like metamaterials, sometimes you can see auxetic behavior. So what it means is like when you stretch the material, you will see an expansion in the orthogonal direction. So it's used. These kind of metamaterials are used in, I think, in crashworthiness applications as well.
Sorry, but it means that they're compressive. So if you have a Poisson ratio, that means that this is a compressive material. So this should be an elastic.
Elastic, not plastic. This is the point.
Yeah, it is. Yeah, of course. I think it's worth mentioning. Yeah. So after the elastic limit, you're not dealing with the Hooke's law, because these all the equations is for Hooke's law. I would say, right?
Yeah.
So
incompressible material models, which is the Leibniz's equations, will go on that area. And one more thing that I would like to say, the previous slide, that I would like to say that stress is a lie actually, because yeah, this is very
why
yeah, the stress actually if you go for the plastic level, for example, you have a really big strain that it depends on which area you are looking for. So Bartol actually will mention about it, but if I go for the stress level, I can go for it for the elastic level. I can definitely just compare some geometries between which stress area could be proven, or I can say that because there is a lots of values in here. We cannot just think about the metal materials. We have very tiny strain but you can just say the loss of stress values, the bigger stress values. You can just compare it because it's a linear system. So if you go for the plastic area, this is really bad choice to comparison between the stress. Actually, you may go for the strain, it will be okay. You can assume that may be perfectly plastic that you can compare, but to also mention about that the initial energy maybe. Okay, that's why I'm just saying that stress is a lie if you go deep down into the material characterization. But there is also, you will go back when you just observe the, for example, load a parameter stress triaxiality, so you will understand that okay, stress is not a lie. This is a different story. Sorry about for interruption. Okay, keep going.
Yeah.
Sorry, please.
Okay, I think we can pass it's just the shear modulus is just describes its resistance to shear deformation. By the way, it's a basic for it's dependent on it's a Hooke's law as well, so it is dependent only in linearly elastic situations. So we can go on. So as we mentioned, the Young's modulus is the slope of the stress strain diagram in linear elastic region. So at the right side, we can say that you can see that there's a brittle material, ductile material. So as you can see, the brittle materials have higher modulus, but really low strain value. So it breaks in a really high strain values, I would say. So yeah, please go on.
Okay.
I think there's more. Yeah, so the yield strength is the the point where our stress strain curves linear region changes to I would say nonlinear region.
Actually.
So
yeah,
that's so yeah, maybe I think Erdi can say so much things about modeling the yield strength. Yeah, for the the material data, I would say when you take it.
Yeah, before the yield strength limit, so there is actually a little bit nonlinear behavior in the material because of the concept of the molecular area. So I will just go. Sorry, too much information. I don't want to go there. Please,
okay.
Go ahead.
You say so. Yeah. Okay. So
I'm
go on.
it.
Please, that's the okay. So I think one of the important thing is the modulus of resilience when you're it is important when you're designing a structure which is under a under repetitive loads, I would say. Maybe in example, maybe it's shock springs or the springs for automotive applications, because there's a certain type of load or load on a when you drive, and you don't want to go for permanent deformation when you're driving normal conditions. So you need to select your material according to it, of course. The other example, maybe it could be on the footwear as well. So it's like if you have a certain deformation on your footwear, it would be maybe it will cause your walking into the instability. So maybe you can fall, right? So yeah, please, we can go on. Yeah. So it is the by the way, the for the thing is the under the modulus of resilience is the linear the energy it can take, the material's energy it can take in the elastic region. Yeah. So
we already know the ultimate.
Yeah, we already know that. Yeah.
But this is important.
It's modulus of toughness is really important in crash worthiness sections also. So what I can give as an example for selecting a carbon fiber material. So some carbon fiber materials has which we will see in chapter 2. So has a high modulus or high strength. If you go to the websites of manufacturers, you will see that. So think about a Formula 1 crash. So it is a really highly dynamic event. So you will not want a structure that's really I think brittle. You want a structure which has a really high strength in order to get a really good energy absorption. So modules of toughness tells us
actually
we need
under the stress strain curve. So I'm saying this because it is from the carbon fiber, because it's really a good way to understand that the selection of material.
So if I say go for example, it's a crazy idea that go for the negative Poisson ratio. What about it? So if we have a negative Poisson ratio in elastic region, so yeah,
okay,
we have an elastic region, so we have a spring for that, but we have a lattice model, as your answer tells, what would you like to say about it?
About the crash worthiness, or
maybe
because there's so the thing is, in my thesis or in my work, what I've seen is it's just you have for the linear elastic region, you're seeing a normal behavior, but when you increase the displacement, what happens is certain local collapses. So and that certain collapses, you are seeing that a softening, I would say softening behavior as well. It is a good thing in the crash worthiness, because
sorry for interruption. This is the hardening area. We can assume this can be a softening area. We can assume.
Yeah.
This is the behavior of the material. We are just separating each other. Sorry, please go on.
So this kind of, I would say this kind of materials is really good in terms of the crash worthiness, because it's there's a certain strategy to keep people safe. So you don't want to have the really high forces when the thing of the crash event happens. So that collapsing action is really important, and it saves lives, I would say. So your selection, you're selecting and sometimes a geometry of the metamaterial according to its collapse mechanisms. So that's it.
So that makes this simulation so important, definitely. As far as I understand here, material selection is the key point, because whatever you design, you basically, with this highly complex softwares, you need to understand this design's behavior. At the end, it's all related with the material properties and material, strength, isn't it? So, well, thank you very much for all this information. And this is how we met, actually, when RD discovered this complex simulations are all related with the material. And it is also, we had this section before with the professionals. Every design, every product start with material. That's how you can reach Total Materia, which is the biggest source in the world.
By the way, webinar is not end yet. We have lots of things. Yeah, I would like to mention. This is not the last slide.
I know, I know. These are all solutions. Well, basically, you can contact to us to get more details. Well,
so you have the microphone, Zaim. Go ahead, please.
So this is Total Materia. Basically, we need a lot of information from Total Materia. This is how it looks. If you didn't use Total Materia before, we have quick search, advanced search, standard list, a lot of different modules to find a lot of different material properties. Well, you can make material list. You can save this list. You can share with the other departments. We have almost 600,000 of material. It's updating and updating every month. So we have just for 3D printing material 4,600. And we have polymers, we have metals and casting materials information. Here is in this example, when you type unumerical or alphanumerical designation of the material, you're going into the material card. Well, in right hand side, it's all belong to this material. Basically, you can see here we have 1063 mechanical properties of this material. Of course, it depends on this material's heat treatment and forms of the material, SN curves that you can reach. A lot of detailed information about the material, because even if it's the same material, different heat treated forms and different thicknesses will give you different mechanical physical properties, which we just was trying to explain how yield strength, tensile strength values are important, and so many different values that you need to have accurate simulation results, right? So all this information in one single source that you can reach. Basically, here it's easily, you can filter all this material properties, and it is also important temperature dependent material values, because your design might work in under high temperatures. So you need to understand materials behaviors in different temperature rates at the same time. You can save this list, you can compare different materials, different behaviors, different properties in the same time. And with one click, you can export this material card over 25 different solvers. So your solvers can import this material card basically real quick. And ANSYS, Abacus, Nastran, LS-DYNA, whatever you use, it's easy to filter and use this material cards to your simulation softwares. This is the most common use scenario of Total Materia with equivalence cross references of this material. Imagine you have IEC standards, American standards material. You want to see the GB standard equivalence. With one click, you can compare this material. You can find the equivalent according to chemical composition or according to mechanical or physical behaviors of this material. So you can save this list. You can share it with your, purchasing department, and you can even control if this material is compliant according to different regulations. So Total Materia is widely used with and industry giants, industry leaders from all around the world. What I can say, Daimler Turkey is our users, and we have an advanced search option. This is the one that I love the most. I can give you actually a real world scenario many of you might recognize. Well, we have already saved advanced search option here. I want you to just pause here to see that basically
To
imagine.
interrupt you, by the way. Sorry, Zaim.
Yeah, sure.
As you can see, there is a end or future in total materia. So Bart already mentioned about it, modulus of elasticity, resilience, and tensile strength, so yield strength. You can just add or an end features that you are just working a material pool. So you can just easily sort it what you need.
Definitely. Especially, imagine you're running a structural simulation on a critical component, maybe part of a retail frame or a motorcycle chassis, and anything like this, and results show excessive deformation, fatigue failure. You realize your current material simply won't hold up. So, but here is the problem. You don't know what material to switch to, right? So you don't know. Basically, you tried one material, you knew that it's going to work, but actually it's not working. You need a more durable material, but it is also has to meet weight contains, be cost effective, so many things more, right? So this is exactly where Total Materia comes in. Instead of searching across shared PDFs, data sheets, or manufacturer website, you go into the Total Materia Horizon platform. You just click the advanced search, and then minimum yield strength you can add. Also, we typed here, as you can see, it's on over 100 centigrade degree. We want the yield strength value over 300 megapascal. We want tensile strength value minimum 500 megapascal. We want impact strength 40 joule, and we want modulus of elasticity value will be minimum 190, right? Plus we added like a little bit corrosion resistance. We don't want carbon content to be more than 1.2 or 1.5, whatever you want. You're basically filtering this material and asking Total Materia to show you from 600,000 material to give you which one of those material can give you this, right? So just go on, and in seconds you will receive the results. So instead of making hours of weeks of search, you have 19 material only can give you this durability. So this is how it's easy to use Total Materia basically. So you can filter this material. You can still compare this material according to mechanical, physical properties. You can check if this material still have fatigue data for you or stress strain curves. You said stress is a lie, but still stress strain curves are very important, I guess. So, right? So we have a lot of information that you can easily use with your simulation softwares. Still, you can compare this material, which one is the lightest, let's say. Still, you can compare which one is the cheapest one, right? So these are also important. If these materials are compliant, this is another issue, especially for automotive and, you know, so we have a lot of tools.
So it's easy to be used in here because you're just the whole data you have, and I can just clearly see that which materials can be behaved. So
Yeah.
which material I need to choose. So
Every design,
at the
every
beginning of
product starts with material. This is very, very important, right?
yeah, at the beginning of this webinar, we are saying that the common sense in the finite element analysis. So if we go for a good input for which we need, so it will be a good output actually. So
Great. Great
okay.
to hear that from the
By the
professionals.
way, Zaim, it's okay. By the way, we are continuing because we don't have
Please go on,
much
of course.
time for this one. So we will go for the frequency response analysis in Nastran. Bartu, are you still alive?
Yeah.
Can you go?
So before the frequency response analysis, we need to say what is the vibration. So the vibration is like a continuous cyclic motion of a structural component. So the stored energy results in inherent natural frequencies. So please go on. We need to define other things. Yeah.
I'm done.
So this is the single degree of freedom structure. So it's a mass damper system. Sorry, mass spring system. So what we are doing in here is just we're solving the equations of motion to understand the the displacements or the angular velocities, or the natural frequency of a structure for this kind of systems. So this is a little bit detail.
Sorry for the interruption, but as we know that Newton says force equals the mass multiplied by acceleration, as we already know that, and also we already know that the undamped free vibration is stiffness and the displacement. So there is another thing that the damping criteria which interact with the velocity. So the equation motion will be dependent on the acceleration, velocity, displacement, which means defined if defined the damping ratio. I mean the damping coefficient, or and the mass also. So if we go for the only undamped solution, then we have a series of that curve like this. So please go on, Bartek. Sorry about it.
So I think you have said everything about the undamped system, but you know, from these we are extracting angular frequency of this system and linear natural frequency of a system. So it's, if we say that what is the natural frequency, is the frequency of which a system vibrates when not driven by an external force. I would say you can define that, right? Define like this.
Yeah, it depends on the material, actually. Direct material, we can assume that because we have a stiffness, which we can relate it with the modulus of elasticity, as you know, and the other thing is mass, and also we can just assume that related with the density. Just if we ignore the geometry, but you know, the geometry is so much things that so it changed the natural frequency. But if we relate it to material, we will need the stiffness and the mass, actually.
Yes, yeah. For this kind of really, I would say, simple solutions, mass spring solutions, you only need a stiffness of the spring. But other than that, it's just for the other solutions, yes. So this is the, I think we can go on because this is the solution of damped free vibration section. This is for your I would say reading after getting the slides from Zaim, I would say. So this is the
actually there is not only the simple geometry, simple systems we have really complex systems in here. So we need to consider about which area need to be considered as a dampened or undampened. What is the total matrix formulation we need to consider about a system? Should we just include everything on our product, or we may go for the for example, the body in white on automotive industry, for example. So we don't want to just add everything in that product. We may just include some elements, some parts that need to be considered, actually. So go on, please, Bartek.
Yeah, so before the frequency response analysis, I think what we need to define is model analysis. So model analysis is give us to then understanding of vibration characteristics of a system, I would say, or a component. So I would say it's a really it's a first step for dynamic analysis, I would say, and it's the most basic. So in the system, we are considering as a free vibration, and it gives us the natural frequencies of our geometry or component, so that we have an understanding about their resonance vibrations, so that we can. So because of that, we can avoid them when we're designing a structure. Or the model analysis, by the way, is really good when you have an assembly for static analysis. So, and if you have a unconverged situation and you don't understand what's going on, so what you can do is you can go for a model analysis. Maybe you have unconstrained sections, which gives a rigid body motion, I would say. Correct me if I'm wrong, Erdi. So it is a really good way to check your analysis, static analysis as well, or dynamic analysis as well. Do you have anything to add, Erdi?
Yeah, you can just say something about the relationship between the. We can just assume that if an analysis can we approach dynamic solution or static solution. It is a really big differences. So just looking for the model shapes, the frequency you can you got extract. So you can say that this need to be a dynamic explicit solution. This could be a static solution at the end. So if you have a very short time dependent forces considering with the compare with the frequency level, so you can assume that this is a dynamic analysis. I can add it. I can also so much things I would like to say, but please go on.
So okay, for the theory of sorry,
we don't have much time for.
Okay.
This is all
so,
terminology of the eigenvalues, eigenvectors. The audience can be just read that. Maybe we can just skip it because
I think we only can add is you cannot use the displacement values from the model analysis, right? I think it's one of the important things because it's not real. It's a representation
yes,
of how our structure will deform. That's the representation.
Yeah.
In certain frequencies, yeah.
So, actually, we talked about it.
Yeah.
We can see the degree of freedom of the geometry. So we can say that mold shape can be much more suitable to deform. We can say that. So we need to just look at our geometry that which and the changes. So we can just say that with different frequency levels, which deformation level we are expecting it. So we will understand at the end of our behavior of the geometry. I want to add the frequency response analysis in Nastran. That there is another solver cards in Nastran Sol 103 that extract your only natural frequencies. But I would like to say that there is a card in the frequency level in here. So if you go for the Nastran FRF, frequency response function extraction, so in the frequency level, you can see just the frec card and with the ID number 6, and you will see that there is a frequency values which Nastran will use. But using this method, the frec tree card, using with the entering with the lowest and the highest frequency level, you can just directly run your analysis at the model frequency levels. And I will also mention about the bias and the cluster features, but this method can save lives actually. So if you don't much more time and you are just running your assembly just directly with the frequency response analysis, you don't need to go for model analysis first. You can just simply include your base model and you can just directly change your whatever it is, the gravity or the forced load or displacement, whatever you want, you can add it, and you can use this card actually. We can also share this maybe we can also share this model actually.
With webinar recordings and other files that could be very useful.
One thing I need to mention about the frequency response analysis. The damping ratio, the damping value of the structure, it depends on which frequency level you are seeking it. Because when you see that the table, damping table, and the zero at the 0 frequency point, your damping value will be 0.05, and up to the 200 frequency level, and also the 0.05. This means that the damping value that is constant between 0 to 300, and also it will be perfectly constant after that frequency level. But you need to consider about the higher frequency levels will be different damping values that you need to consider about. So it will just a few slides left and I will finish. Just a sec, please. And here's the factory card. You can also reach the documentation, not from documentation, I think. There is a usage of the factory card, and here is the frequency levels 10 or 20. So there is a cluster method, which means it's like a biasing, something like that. If you just enter the cluster, I mean this area, so you will just linearly separated frequency responses, and if you don't if you have any bias, you can just skip it, or maybe you can directly use the different frequency ranges. But this code can easily apply, you can use it actually. So this is the end from my side.
Great.
Anything to add by your side, Bartu, by the way?
I think no. I think that's really
any
good for
questions?
introduction.
Okay, Zaim.
Thank you. Thank you very much for joining us today for the first session of our webinar series. Remember, this is the first one. Well, obviously, Total Materia is more than just a database here. It's an engineering decision engine that eliminates guesswork, right? So you need more accurate information, definitely. It saves time, brings confidence in your FAE projects. If you want more, improve the accuracy of your simulations, reduce risk, and select the most suitable material faster. So here we are. Total Materia is a must-have tool for precision engineering team. Obviously, you can use with this software. With your highly complex simulation softwares, you can contact us. I'm going to share with you my credentials and webinar recordings, and including all this presentations and other files too. So just move to the previous slide. As a reminder, we will be online again next week, May 8th of May, on Thursday, same time. And the third session will be on May 15th. Thank you very much. Thank you, RD, for the amazing examples and so many informations. And thank you very much, Bartu, for you to find time for us today. Thank you very much, guys. See you next week.
See you.
Thank you.
Next week.
See you next week. Yeah.